Without doubt, the human eye is the most remarkable of all optical devices. Here we show some of its main anatomical features. The eyeball is approximately spherical with a diameter of about 25 millimeters. Light enters the eye through a transparent membrane called the cornea. This membrane covers a clear liquid region called the aqueous humor, behind which are the iris, the lens, a region filled with a jelly-like substance called the vitreous humor, and finally, the retina. The retina is the light-sensitive part of the eye, consisting of millions of structures called rods and cones. When stimulated by light, these structures send electrical impulses via the optic nerve to the brain, which interprets the image detected by the retina. The iris is the colored portion of the eye and controls the amount of light reaching the retina. The iris acts as a controller because it is a muscular diaphragm with a variable opening at its center through which the light passes. The opening is called the pupil. The diameter of the pupil varies from about 2 to 7 millimeters, decreasing in bright light and increasing or dilating in dim light. Of prime importance to the operation of the eye is the fact that the lens is flexible, and its shape can be altered by the action of the ciliary muscle. The lens is connected to the ciliary muscle by suspensory ligaments. We will see shortly how the shape-changing ability of the lens affects the focusing ability of the eye. Optically, the eye and the camera are similar. Both have a lens system and a diaphragm with a variable opening or aperture at its center. Moreover, the retina of the eye and the image sensor in a camera serve similar functions, for both record the image formed by the lens system. In the eye, the image formed on the retina is real, inverted, and smaller than the object, just as it is in the camera. Although the image on the retina is inverted, it is interpreted by the brain as being right side up. For clear vision, the eye must refract the incoming light rays so as to form a sharp image on the retina. In reaching the retina, the light travels through 5 different media, each with a different index of refraction, n. The path of a given light ray starts in air with n equal to 1.00, through the cornea with an index of 1.38, into the aqueous humor with n equal to 1.33, through the lens with n equal to 1.40, and finally, through the vitreous humor with n equal to 1.34 before reaching the retina. Each time light passes from one medium into another, it is refracted at the boundary. The greatest amount of refraction, about 70% or so, occurs at the air-cornea boundary. According to Snell's law, the large refraction at this interface occurs primarily because the refractive index of air with n equal to 1.00 is so different from that of the cornea with n equal to 1.38. The refraction at all other boundaries is relatively small because the indices of refraction on either side of these boundaries are similar. The lens itself contributes only about 20 to 25% of the total refraction, since the surrounding aqueous and vitreous humor have indices of refraction that are nearly the same as that of the lens. Even though the lens contributes only a quarter of the total refraction or less, its function is an important one. The eye has a fixed image distance. That is, the distance between the lens and the retina is constant. Therefore, the only way that objects located at different distances can produce sharp images on the retina is for the focal length of the lens to be adjustable. It is the ciliary muscle that adjusts the focal length. When the eye looks at a very distant object, the ciliary muscle is not tensed. The lens has its least curvature and, consequently, its longest focal length. Under this condition, the eye is said to be fully relaxed, and the rays form a sharp image on the retina. When the object moves closer to the eye, the ciliary muscle tenses automatically, thereby increasing the curvature of the lens, as we see here, shortening the focal length and permitting a sharp image to form again on the retina. When a sharp image of an object is formed on the retina, we say the eye is focused on the object. Accommodation is the process in which the lens changes focal length to focus on objects at different distances. When you hold a book too close, the print is blurred because the lens cannot adjust enough to bring the book into focus. The point nearest the eye at which the object can be placed and still produce a sharp image on the retina is called the near point of the eye. The ciliary muscle is fully tensed when an object is placed at the near point. For people in their early 20s with normal vision, the near point is located about 25 centimeters from the eye. It increases to about 50 centimeters at age 40, and to roughly 500 centimeters at age 60. Since most reading material is held at a distance of 25 to 45 centimeters from the eye, older adults typically need corrective lenses, glasses, or contacts to overcome the loss of accommodation. The far point of the eye is the location of the farthest object for which the fully relaxed eye can still produce a sharp image on the retina. A person who is nearsighted or myopic can focus on nearby objects but cannot clearly see objects far away. For such a person, the far point of the eye is not at infinity and may even be as close to the eye as 3 or 4 meters. When a nearsighted eye tries to focus on a distant object, the eye is fully relaxed like a normal eye. However, the nearsighted eye has a focal length that is shorter than it should be, so rays from the distant object form a sharp image in front of the retina, as seen here, and blurred vision results. The nearsighted eye can be corrected with glasses or contacts that use diverging lenses, as shown here. The rays from the object diverge after leaving the eyeglass lens. Therefore, when they are subsequently refracted toward the principal axis by the eye, a sharp image is formed farther back and falls on the retina. Since the relaxed but nearsighted eye can focus on an object at the eye's far point, but not on objects farther away, the diverging lens is designed to transform a very distant object into an image located at the far point, as shown here. Let's do a simple example that illustrates how to determine the focal length of the diverging lens that accomplishes the formation of the image of a distant object at the far point of a nearsighted eye, thereby correcting the nearsighted vision for distant objects. Suppose a nearsighted person has a far point located 715 centimeters from the eye. If their eyeglasses are to be worn 2 centimeters from the eye, find the focal length needed for the diverging lenses of the corrective glasses so that the person can see distant objects. To solve this, we see that, since the glasses are to be worn 2 centimeters in front of the eye, the far point is 713 centimeters to the left of the diverging lens, assuming both eyes have the same degree of nearsightedness. The image distance is therefore DO equals negative 713 centimeters, where the negative sign means to the left of the lens. The object is assumed to be infinitely far from the lens to the left. Applying the thin lens equation, we have 1 divided by f equals 1 divided by DO plus 1 divided by DI. This equals 1 divided by infinity plus 1 divided by negative 713 centimeters. Solving for f gives f equal to negative 713 centimeters, which is negative as expected since the focus was supposed to be located at the far point, which is to the left of the lens. A farsighted or hyperopic person can usually see distant objects clearly, but cannot focus on those nearby. Whereas the near point of a young and normal eye is located about 25 centimeters from the eye, the near point of a farsighted eye may be considerably farther away than that, perhaps as far as several hundred centimeters. When a farsighted eye tries to focus on a book held closer than the near point, it accommodates and shortens its focal length as much as it can. However, even at its shortest, the focal length is longer than it should be. Therefore, the light rays from the book would form a sharp image behind the retina if they could do so, as shown here. In reality, no light passes through the retina, but a blurred image does form on it. Farsightedness can be corrected by placing a converging lens in front of the eye, as shown here. The lens refracts the light rays more toward the principal axis before they enter the eye. Consequently, when the rays are refracted even more by the eye, they converge to form an image on the retina. The lens is designed so that the eye perceives the light to be coming from a virtual image located at the near point, as we see here. Consider the following example that illustrates how the focal length of a converging lens is determined to correct for farsightedness. Suppose a farsighted person has a near point of 330 centimeters from the eyes. Obtain the focal lengths of a pair of converging contact lenses needed to read a book held at a distance of 25 centimeters from the eyes and contacts. Since the contact is against the eye, the object distance is 25.0 centimeters from the lens, and the image distance is negative 330 centimeters to the left of the lens. The focal length can be determined from the thin lens equation as 1 divided by f equals 1 divided by d0 plus 1 divided by di, which equals 1 divided by 25.0 centimeters plus 1 divided by negative 330 centimeters. Solving for f gives f equals 27.0 centimeters. Finally, The extent to which rays of light are refracted by a lens depends on its focal length. However, optometrists who prescribe correctional lenses and opticians who make the lenses do not specify the focal length directly in prescriptions. Instead, they use the concept of refractive power to describe the extent to which a lens refracts light. The refractive power of a lens is measured in diopters and is given by 1 divided by the focal length in meters. The unit of the diopter is therefore inverse meters. This relation shows that a converging lens has a refractive power of 1 diopter if it focuses parallel light rays to a focal point 1 meter beyond the lens. If a lens refracts parallel rays even more and converges them to a focal point only 0.25 meters beyond the lens has 4 times more refractive power, or 4 diopters. Since a converging lens has a positive focal length and a diverging lens has a negative focal length, the refractive power of a converging lens is positive and that of a diverging lens is negative. In our nearsighted example, the focal length of our diverging lens was equal to negative 713 centimeters. The corresponding refractive power in diopters is 1 divided by negative 7.13 meters, which equals negative 0.140 diopters. In the same way, the focal length of our converging lens in our far-sighted example was 27.0 centimeters. This corresponds to 1 divided by 0.270 meters, which is equal to 3.70 diopters.